introduce one of our newer colleagues in the engineering college, Professor Uday Shambag, who started in the IOE department last fall. But before then, he had tenured positions at Penn State and at Illinois. And now he's going to tell us all about optimization.
Thank you, Jim. Thank you again for the invitation. It's a wonderful group to present in front of, so I'm quite grateful. Okay. Oh, hang on. Okay, so this is going to be work on zeroth order methods, and essentially these types of methods have assumed relevance, I would say over the last 10 to 15 years. And the focus today is going to really be on trying to show the relevance of such methods in dealing with a host of complexities, ranging from stochasticity, non-convexity, and even hierarchy. Okay, and so let's begin. And this is actually a lot of it is joint. I mean, all of it is joint work, and I'll specify where. Okay. So the first part of the talk is going to focus on non-smooth, non-convex stochastic optimization. Right. So we're looking at problems like these, where f is expectation valued, and f tilde for a given psi is assumed to be Lipschitz continuous. Okay, L0 Lipschitz for almost every psi. For the purposes of this talk, we'll be assuming that X script is a closed and convex set, which I can project onto if necessary. Okay. Let me just give you a quick blurb on work done in non-smooth, non-convex stochastic optimization. So amongst the earliest work that at least we know of was work by Jim Burke with Mike Overton and Adrian Lewis. This is in 2005, the gradient sampling work. And there's work where folks have looked at structured non-convexity, which is work by Yang Xu and Wotao in 2017. There's work, of course, the very well-known paper by Saeed Ghadimi, George Land. And amongst the papers that we'll be kind of referring to is the work by Yuri Nesterov and Spokojny, which really looks at zeroth order methods with Gaussian smoothing and provides refined guarantees. Okay. This result is particularly important because for non-smooth, non-convex, unstructured optimizations, the paper by Zhang and al. Actually provides a negative result. It tells you, now I'll actually go into that next. So this is the result in Zhang et al. It says there's no finite time algorithm that can compute epsilon stationary points of non-smooth, non-convex optimization problems, okay, which have Lipschitzian properties. Okay, so that immediately tells you that you don't have access to stationarity. Okay, and so the question is, and you can see that this is what we do for smooth non-convex, right? We're looking at trying to compute epsilon stationary points in finite time. But this negative result precludes us from doing that. And so the question is, how do we proceed? Okay, and so the way we proceed is via smoothing. Yeah.
For every problem, or is it worst case?
No, it's for every problem. Yeah.
For every
Yeah. As long as you have Lipschitzian properties, that's all you have. Okay. So I'm going to just remind you what the definition of directional derivative is. I'm not going to kind of belabor this here, but this is the definition of a directional derivative. And using the directional derivative, you can define what is called the Clark generalized gradient. Okay. So Clark calculus and Clark stationarity has been a particularly useful object when dealing with non-smooth optimization. And Clark stationarity is only one type of stationarity. You have all sorts of other stationarity notions. Clark, I should say, is amongst the weaker forms. Okay, and so one of our efforts is to try and now look at more refined notions, and I'm not going to do that in this talk, that go beyond Clark. But for the purposes of this talk, we'll be focusing on Clark. Okay, so just to remind you, if the function is differentiable, the Clark generalized gradient reduces to the standard gradient. If the function is convex, the Clark generalized gradient reduces to the convex subdifferential. Okay? So if H is L0 Lipschitz, this is well known, that the Clark generalized gradient is a non-empty convex and compact set, and the elements of that set are bounded by L0. You can say something about the upper semi-continuity of this map. What we're interested in is this enlarged Clark generalized gradient, which essentially says, so the partial of delta of h of x in a delta sense, or the delta enlarged Clark generalized gradient, is the convex hull of zeta, where zeta lies in the Clark generalized gradient of y, where y is within delta of the point in notion, the point in question. Okay? And so this is what we can actually focus on, and it can be viewed as the convex hull of elements in a neighborhood. Okay, loosely speaking. Okay, so that's the object we're interested in. Okay, so what is our focus? So we started this right during COVID. So this is 2021, together with my now he's my colleague at Rutgers. He was my doctoral student together with Angelia Nedic, Farzad Yousefian. We started working on trying to use zeroth-order methods for computing approximate stationary points in this sense for non-smooth, non-convex stochastic optimization. And this work then has kind of evolved, and now we've added kind of quasi-Newton schemes on top of that. So we'll talk about it. Okay, so the idea is to replace the non-smooth problem with a related smooth problem and relate the solution of the smooth problem to that of the non-smooth problem. Okay? Okay, so and it's interesting, when we first worked on this, so we've been working on these types of smoothing techniques since 2010 or 2011. I remember in our first paper when we wrote this, one of the reviews we got back told us that, the person told us that basically this goes back to the 1900s with Steklov and Sobolev, the notion of convolution smoothing. It's quite remarkable how far back some of these ideas go. Okay, so this notion of randomized smoothing essentially says, given a Lipschitzian function, I can define a smoothing, an eta smoothing, such that the value of the function, the smooth function, is the expectation with respect to u over some set. If it's using a Gaussian random variable, this is called Gaussian smoothing. If it's with respect to u being in a ball, then it's called spherical smoothing. Okay? And in this particular case, B is the unit ball, and you can compute the gradient of this. Well, at least you can specify what it is in an expected value sense. Okay, so this is one type of estimator, right? There's a lovely paper by Albert where they talk about different estimators, right? This is often called the central difference estimator. There's a forward difference where this is just f of x. There are different types of estimators, and actually they have slightly different properties. And it turns out that the bounds you get are closely tied to the type of estimator. There are certain estimators that you actually get inferior bounds that at least we have found difficulty in improving. Okay? But if you're really interested, Albert's got some wonderful work in terms of trying to show, and I apologize, I don't have that reference here, but I can give it to you offline, where they look at the quality of the gradient approximations for different types of estimators. Okay? So this is the gradient, but of course, this cannot be evaluated in finite time because you need to take that expectation. Okay, so you don't have that. But what this does is it suggests an estimator.
Wait,
Yeah.
so that I can follow.
Yeah.
Are you putting a uniform distribution on that?
So this, but wait, sorry, what happened to this thing? Sorry. Oh, it's gone to some continuous growth. Okay. So this one, so in this particular case, this is uniformly distributed on the surface of the sphere. Yeah. Okay. Okay, so there are some properties of spherical smoothing that some of which precede us and some which we've refined, right? So essentially what you know is that h eta can be shown to be C1. That's the definition. If the original h is C00, which means that it's merely continuous with Lipschitz, it's a Lipschitz continuous function with constant L0, then you can say something about the smooth counterpart. You can say something about the quality between the smooth counterpart and the original counterpart. This actually bound has been improved to square root n. So one of the big challenges when you use zeroth order methods is A, computing the estimator, and B, assessing the impact of dimension dependence. Okay? And so when we first did this, it turned out that the bound that we got was n. Okay? But it turns out that if you use this concentration inequality, Levy's inequality, you can improve that to square root n without any change in the estimator. Now, I should say that that holds for this central difference estimator. If you use a forward difference estimator, it's unclear if you get this. Okay, so we've tried, and there have been other papers that have referred to this where they've also not been able to get the improvement. Okay, what is also important is the second moment of the gradient estimator, the original bound was n squared. With the Levy inequality, the concentration inequality, you can improve this from n squared to n. Okay, so so this result precedes us. This bound, actually, we were able to kind of refine. There's a paper by Jordan where they kind of hand wave around and say there is a bound, but we're able to actually do it with by induction and get a clean bound. Yeah.
These results are for any eta?
This is for any eta. Yeah. Okay. So for those of you who are not familiar with this, if I give you a piecewise linear function, that's an eta, you can see that it just gets closer and closer. Okay. So our focus is on minimizing f eta. But if you minimize f eta, you need to be able to say something about the solution to the original problem. Okay. And that's where this result, so I should have actually had the references here. This is a paper by Goldstein in the 80s. And what Goldstein's result tells us is that if you get a solution to the smooth problem, it's actually a solution using the enlarged Clark generalized gradient of the original problem. Right? So if I give you a solution to the smooth problem, that's not enough, right? I need to know how it related to the original problem. So from your standpoint, what you should be reading this as is if the original problem was convex, then this essentially is a stationary point associated with the epsilon convex subdifferential instead of the original subdifferential. Okay.
Does that also imply a bound between solution you converge to and the stationary?
We mean the original stationary point?
Because there is a delta, right? The difference. So
Yeah. No, all you can get is this relationship. So are you saying?
So in the definition of
Yeah.
the subdifferential sub,
Yeah. There's a delta. Yeah.
right?
Yeah.
That already implies that you're delta close.
Right.
Yeah.
Well, so you'll be careful. It doesn't say you're delta close. What it says is that you're using points which are within delta of the original x to construct this convex hull. So you have to be a little careful about making that claim. However, you can prove consistency of these estimators, but that's not the way you would do it. Okay. So one of as optimizers, we're always interested in constraints. And so if you're looking at constrained problems, this is a metric of stationarity for the constrained problem, right? It's just the standard projected gradient residue. Okay, so where instead of f, you have f eta. Okay. And so this is a very kind of simple method. Right? This is just using a mini batch of samples from the surface of the eta sphere, compute the zeroth order gradient estimator, and update xk. So this was our first kind of paper that we wrote on this, and using this you can actually get complexity bound. So this was the result from Jordan and subsequent results, and these results are in unconstrained regimes. They don't have an almost sure convergence guarantee. So we're able to get very similar kind of guarantees. You can see that our iteration complexity is better, but our sample complexity is a little worse in one of the cases. And the reason why the iteration complexity and the sample complexity differ is because you're using a mini batch setting where the sample size is growing, but not at an absurd rate. It's growing at the rate of k. So if k is the iteration index, it grows at k raised to 1 plus delta or something. Now, it turns out that you can actually show asymptotic convergence to the solution of the smooth problem. Okay, so you can do that just by kind of using diminishing step lengths. One of the challenges with this is, of course, you need to know L0, right? That's in fact something that plagues most such schemes, yeah.
With a fixed data. So
This is the fixed data. In this particular case, and I'm going to talk about diminishing eta later. This is not a diminishing
you
eta.
get to the exact solution you're saying with a diminishing steps.
No, I'm not getting to the exact, I'm getting exact solution of the smooth problem. Of the smooth problem.
Yeah.
Okay?
Is that an optimal trade-off or are there different trade-offs with sample complexity versus?
So when you say a trade-off, so essentially what happens is that the way we design these parameters is based on, so one issue is that when you choose these step lengths, you have to be a little careful. If you choose them without recognizing the dimension dependence, you get a pronounced dimension dependence of the sample complexity. You get n raised to 5. Similarly, you need to also be cognizant of eta when you choose the sample, the sampling rate and the step length sequence. Both can be kind of controlled. Okay. So second part of this paper focused on quasi-Newton schemes. Now, there's a fair amount in this, and I'm not going to spend as much time on it. So I'm going to be kind of moving through this part a little faster, and I apologize for that. This is merely to kind of show you that quasi-Newton schemes can also be addressed using this framework. But the goal is to also just show you some numerics to relate and introduce this type of method. So for those of you unfamiliar with the quasi-Newton framework, essentially it can be traced back to the seminal papers, individual papers by Broyden, Fletcher, Goldfarb, and Shano in 1970. And the idea was to basically be able to construct a sequence of iterates using these approximations, Hessian approximation, Hessian inverse approximations, and a step length sequence. And in deterministic, strongly convex regimes, you're able to get superlinear convergence just using first derivatives. Okay, it's one of the kind of major findings of QN methods, right? And one challenge has been, and the nice property was that you have the self-scaling adaptive structure. And so that's been one of the reasons why quasi-Newton schemes have assumed relevance. So the earliest work there has been work by Horeno Sedal and his co-authors, and Arun Mokhtari and Rivero in 2015, where they looked at strongly convex problems. Since then, there was some follow-up work by Jordan and others, and our work with Angelia and Farzad looked at moving this to merely convex, okay, by incorporating an iterative regularization. There's some follow-up work with this where we looked at certain forms of non-smoothness and variance reduction. I won't focus on that here. The focus today is really on non-smooth, non-convex. So in the case of non-convex but smooth, there's work done by Don Goldfarb, Chichian Ma, and their co-authors, and the focus of this work has been on smooth, deterministic, unconstrained, but non-convex. And here what you need is you need actually F to be C2. You need the function to be twice differentiable, and you need bounds on the eigenvalues, a priori, okay? The work by Frank Curtis and Che, I'm not sure I'm pronouncing correctly, is drops smoothness and looks at using gradient sampling to come up with asymptotic guarantees. There's also some recent work by Raghu Bolagaprada and Stefan Wild, and they've weakened some of these assumptions. And again, they have an adaptive sampling scheme, but to the best of my knowledge, these are asymptotics, okay? Our focus really has been to weaken all of these. One of the challenges when you're dealing with quasi-Newton schemes is that you need to, at least if you're looking at constraint settings, you can take quasi-Newton schemes and customize them if you have very structured constraints. But in general, that's hard to do, right? And so what we did, which was quite, I would say, naive, okay, is to just use Moreau smoothing to get rid of the constraint and provide a bound on the infeasibility in an ex-post fashion. Okay, and I'll provide some clarity regarding that. All of you are familiar with the Moreau envelope. Essentially, what I do is I had the X script here. I essentially replace this F eta by the expectation of the original F tilde eta, and I use the gradient of the Moreau envelope there. So, and essentially what this does is it has two types of smoothings. Now you might say, why didn't I directly use smoothing on this? Well, you don't have the Lipschitzian structure with the indicator function of the convex set, right? So you can't use direct smoothing. You have to do something else, okay? And so using this, you can have a very similar scheme where you use a mini batch again, you generate this Hessian approximation, and this is why describing this in a short period of time is hard, right? So because coming up with a smooth BFGS scheme is quite elaborate, and this itself will take me quite a bit of time to explain. So that's not my goal today. But suffice to say, we've been able to extend BFGS by combining smoothing, combining mini batch sampling to come up with a framework for which we can provide eigenvalues. The whole point is you need to be able to get bounds on the eigenvalues of HK. Okay, and the reason you need that is when you do the analysis, these pop up. And in fact, these need to be known a priori so that you can actually use them within the algorithm, okay? And so you can see this P, which I haven't defined, is the memory, okay? So these are the eigenvalues associated with the HK. What is the HK? HK is this matrix that is part of the update rule. So this matrix is something that I construct. Actually, I construct the BK. The HK is the BK inverse. Okay, and I need the eigenvalues of this because when I do the analysis, I need to know whether indeed I get the required properties. Okay, so now let me just remind you how we compare to related work here. Essentially in this work, so there's work done by Don Goldfarb, Raghu and Albert with Horinosa and Martin Takach. And essentially in this particular setting, I assume that F is neither C1 nor C2, right? But the smooth counterpart, of course, is C1, and it's got Lipschitz continuous gradients, but of course we don't have C2, right? Now the work by Don Goldfarb, they have a priori eigenvalue bounds that they're able to provide, okay, in an explicit fashion. And essentially, now you might remember I said something with the Hessian having, but these are not the bounds on the Hessian. These are the bounds on the constructed matrix, okay? Now, to the best of my knowledge, the work by Raghu and Albert, they have constants that they prescribe exist. We've been able to actually refine and isolate these constants because these constants are necessary for us to prescribe the step length schemes, the step length sequences.
Right. All of these are limited memory schemes, right?
Yeah.
You cannot do it if you have full memory, right?
I don't think so. At least I don't want to say I don't think so. I haven't been able to do it. Yeah. Okay. So then, and so in this particular case, you can get similar guarantees. And here, you can get a bound on the infeasibility. Again, you need to use that concentration inequality to improve this from n to square root n. Originally, we could only get n. And with this concentration inequality, we've been able to improve it to square root n. Now, you can actually derive complexity guarantees. In this particular case, what we've done is we've tried to come up with complexity guarantees which are memory invariant. That doesn't mean the memory can go to infinity, by the way. It just means that these are memory invariant. Now, you could do it differently and show the impact of memory. And you can see that the complexity guarantees in terms of the constants are significantly worse. And the reason is you're trying to deal with these eigenvalues, right? Now, that doesn't necessarily mean that the scheme does much, much worse. So for instance, what we did was, if you look at this rather simple problem, a min of 2 quadratics, we've got other numerics in the paper. You can see that the SQN scheme, in terms of empirical behavior, outperforms in general. I mean, not just for these. No, I don't mean in general. I mean, for these problems, it does quite well. Okay? I don't want to make a sweeping statement here, but it does quite well. And what I want to point out is this interesting graph. So if you look at stochastic gradient schemes, most of you here who work with SGD know that you see this jagged behavior. It's actually a distinct characteristic of using SGD. But it turns out that if you use, at least in this setting, if you use SQN, SQN has a self-scaling structure where it doesn't take these full steps, it scales. And you can see far better behavior, okay? Now, I don't want to, because we haven't done much broader testing, right? But I have to say that SQN's behavior tends to be far better than the promises that the complexity guarantees provide, okay? So this work is currently under revision. And it's with Luke Marin, my doctoral student at Penn State, and Farzad, who's at Rutgers. Okay. Okay, so the second part of the talk is going to focus on hierarchical problems, where we again use this convolution smoothing structure to deal with a class of problems called mathematical programs with equilibrium constraints. Now, because not everyone in this room will be familiar with the variational inequality problem, I just thought I'd give you a quick blurb of the variational inequality problem. The variational inequality problem requires, given a set Y script and a mapping F that goes from Y script to Rn, the variational inequality problem requires a Y hat such that Y hat minus Y transpose, the mapping F is non-negative for all Y in the set, right? And so this can capture a whole host of problems, ranging from convex optimization problems, non-cooperative games with convex strategy sets and smooth payoffs, and a range of equilibrium problems, including the Wardrop equilibrium problem, subclasses of traffic equilibrium problems. There are a whole host of problems. Okay, so if you had, for instance, this problem, where H is C1, then Y is a minimizer of C opt if and only if Y is a solution of VI, Y script, and the gradient map of H. Okay, now when H is expectation valued, then we often refer to this variational inequality problems as stochastic variation, because essentially evaluating the map is difficult, right? You can only construct estimators. If, on the other hand, you had an equilibrium problem, where essentially every player is looking to minimize her objective given rival decisions, then this tuple is a Nash equilibrium. It's an NE if and only if Y is a solution of this variational inequality problem, where this map is a concatenated gradient map. Okay, so there are a host of such problems you can construct. And so now you can construct a parametrized variant of this where X is some decision that is taken at the upper level, right? A classical setting where this occurs is the Stackelberg equilibrium problem. You have a collection of followers that are competing to reach an equilibrium. There's a leader that makes a decision, either ahead of time or in a one-shot basis, okay? So this leads to what is called a mathematical program with equilibrium constraints. Minimize f of xy subject to x being an x script and y is a solution to this VI. Now, some of you might say, well, this looks a bit like the bi-level problem. And indeed it does. There are some distinctions, however. Most bi-level problems that people can actually address use the implicit function theorem to eliminate the lower level, at least the recent efforts in terms of complexity and rate statements. We cannot do that, right? In our case, we can't do that. We have constraints, right? And we don't have these types of assumptions that the solutions are in the interior, okay? So this is the problem of interest. I'm interested in minimizing f in x comma y such that y is in the solution set of this parameterized variational problem, right? And there are a host of applications of these, right? So this subclass of bi-level problems, Stackelberg problems, frictional contact problems, market design, so there are a host. In fact, there are monographs on this. This is the well-known monograph by Zhongxi Pang, Tom Luo, and Danny Ralph. Those of you interested, Zhongxi is going to be visiting next week. I know some of you are going to meet him. He's giving the MICT lecture, so this is a plug for that. So this book came out in '97. Okay, so this field is relatively mature. And there've been a host of papers in this area on coming up with extensions of standard nonlinear programming schemes. The challenge with applying standard nonlinear programming techniques to this problem is that this problem fails to satisfy standard constraint qualifications. LICQ, Mangasar and Frumowitz, any of these. So standard NLP techniques cannot be directly applied because you don't have necessary conditions of optimality. However, using penalization, regularization, you can get around that. But almost all of this work has just provided asymptotics, right? And of course, it's in deterministic regimes. Okay, so this is, of course, just a smattering of the work. Okay, and there are no available non-asymptotic guarantees. So when we started working on this again, during the COVID period, there were no asymptotic guarantees even for the deterministic setting. Okay, sorry, non-asymptotic, I meant. So I'm interested in two problems. One is called the single stage problem. I'm not going to do both, I'll just do one of them today, where essentially you make decisions X and Y simultaneously. And the second is called the two-stage problem, where essentially the followers, if you will, reach an equilibrium and the leader makes a decision knowing the type of equilibria that will emerge, right? So the follower knows the structure of the equilibria and essentially knows that each y omega is going to be in this regime and chooses to minimize this, where y omega can either be a single valued map or it could be a multi-valued map. Okay. Now, in this particular setting, the one difference in our work is going to be that we are going to assume that this lower level problem has a unique solution. In fact, it has a strongly monotone map. And the reason that I do that is because we're going to use an implicit approach. Okay, and I'm going to show you what I mean by that. Essentially, I'm going to be able to write the original problem as f of x comma y of x, where y is a map that gives you the solution of the lower level problem given x. Now you might say, well, if you have that, you're done. No, you don't have gradients, tractable gradients, even if you assumed magically that you could get differentiability. Okay, and so again, we leverage smoothing. Okay, and so essentially what we do here is we can construct an estimator f eta in this form. So you can actually prove that this function is Lipschitz continuous under some conditions. You need f to be Lipschitz, you need y to be, so solution maps, single valued solution maps can be shown to be Lipschitz continuous under a classical result from the 80s by Stella de Formos, right? So you can use that. So you can show this is Lipschitz. Using that, you can construct this kind of smoothing. Now note here, you need to have this randomness both for x here and within the y. Okay, so this makes it a little harder. Okay, so randomized smoothing, again, this has a long history, goes back to, I don't even have the reference by Sobolev, okay, but there are, and so here's a naive projected gradient approach. It's a naive approach, and I'll tell you why it's naive. The problem is that I don't have access to y of xk, right? This I don't have access to, right? And so I don't even, I don't have access to a subgradient. So this obviously is neither implementable nor is it a well-defined scheme, right? So the idea is, okay, use spherical smoothing. I'm not going to belabor this. We did this in the previous part, right? And so then you say, okay, instead of using that gradient or the gradient estimate, the smooth gradient, use a gradient estimator. But there's still a problem. The gradient estimator as constructed before requires y of xk, which I don't have. Y of xk requires an exact solution to a stochastic problem in finite time. I don't have that, right? And so what do I do to address that? Well, what I do is I introduce, so first I've got this eta k. The second thing I do is I get an approximate solution epsilon k, y epsilon k to the second stage, to the lower level problem. And how do I construct that? I can construct that using stochastic approximation. Okay, so I can essentially take big O 1 over epsilon k steps in an auxiliary stochastic approximation scheme that gives me a y epsilon k of xk, which is of course a random variable. And this random variable satisfies this mean square bound. Okay, now the issue is that this epsilon k here is not necessarily conditionally zero mean, right? This is a biased estimator, right? And so you have to be careful about it. It's not as simple as just introducing this. And so this is how you construct this, is just a standard stochastic approximation framework for resolving the stochastic VI. You get an approximate solution. If you use mini-batch schemes, you can actually get linear convergence, right? So you can get it quite fast. Okay, and so this is what you have, right? This is the estimator you construct. Again, it's not conditionally unbiased. You have to be a little careful about this. So when you do the analysis, so you have to be able to derive moment bounds which capture both the eta and the epsilon here, okay? And you need to control this. This epsilon has to be driven to 0, okay? And so we go ahead and do that. I'm not going to kind of bore you with the details, but you can derive rate guarantees and complexity guarantees for this, both in terms of upper level evaluations and lower level evaluations. This is more just kind of machinery, right? I don't want to kind of, and this is for the case where the original implicit function is convex. And I should say that that is not entirely unheard of, right? It happens in a lot of Stackelberg settings. You can actually prove convexity of the implicit function. Yeah. Go on, Albert.
M is your step size, right? Eta is your parameter.
Yeah.
What's happening to epsilon k that you had?
So epsilon k in this particular case, where did I? So maybe I didn't specify it here. I'm not specifying it's tied to one of these. So you need to get increasingly unbiased estimator. I may have misputting that there, but yeah.
The same order as epsilon or not?
So epsilon k is going to be of the same order as gamma k. I don't know if it's square root gamma k or something, but it's around the sort. I can't quite recall. Okay, so this is for the convex regime. And in fact, you can use an accelerated scheme. Okay, so you can actually introduce an accelerated scheme where you need to deal with this bias, but you need to kind of, again, do it in a fashion which reflects the step lengths and the smoothing iterates. Okay, and so for the accelerated scheme, you get the Nesterov bound of 1 over k. So this is a non-smooth convex optimization problem if the implicit function is convex. And you get a near optimal sample complexity. Okay, now if it's not convex, we do what we did before, right? So if it's not convex, now it's non-smooth, non-convex. The smoothing gives you a stationary point that has some relationship to the original problem in terms of the enlarged Clark generalized gradient. Okay. Okay, so this part is repetitive. Okay. Okay, and so this is the result that I was mentioning. If you get a 0 of the residual function, that implies that 0 is a stationary point of the smooth function plus this is the normal cone, and which implies that it satisfies stationarity with respect to the enlarged Clark generalized gradient. In fact, turns out this 2 is not necessary. We realized that in our revision, you don't need the 2, it's just eta. Okay.
So in the smoothing, you don't have exact access to yx, right? So how do you?
So y of x is obtained using the auxiliary stochastic approximation scheme.
Even for the smoothing, you're doing that.
Yeah, you don't have a choice because the y of x is just not available to you. You need to kind of do that. So once you have that, okay, so these, and then you can get similar statements for the non-convex version, which is what I have. And then this is an instance of a problem which I just want to show you. Compare this to established schemes for solving MPEX, right? So there are established schemes. Albert's advisor, Jorge Nosedal, has Nitro, which is well known for solving MPEX. And there are others. Okay, so let's talk about these schemes. So essentially, when the problem is convex, the implicit problem is convex, you can see the difference between our scheme and Nesterov scheme. Nesterov scheme has fixed smoothing, so it only gives you approximate solutions. Our scheme has diminishing smoothing sequences, so you get asymptotically exact solutions. Okay. If you use the unaccelerated version, it doesn't do too badly, but the accelerated version, of course, does better. And here's the interesting part of using. So the de facto approach for dealing with MPEX, stochastic MPEX, has been sample average approximation. So this goes back to work by Alexander Shapiro, right? So what they do is, you've got an expectation. I write down the necessary and sufficient conditions of optimality and have a large mathematical program with complementarity constraints. I then replace the expectation with a sample average, and then I solve that once to get one element, and I do it many times to construct some sort of mini batch estimator. If you just solve the problem once, you can see that this becomes increasingly untenable, okay, using sample average approximation. And this scheme, of course, scales a lot better. Now, what you want to also observe is the following. I don't know whether I have the Barron. Okay, I want to point this out. So one challenge with MPEX is that if you wrote down the optimality conditions, so for instance, if I gave you this problem, minimize f of xy, just for a simple problem where I say y is a solution to a problem, so y comes from here, let's say. Right? And if I just said this, something very simple, okay, and I have some D transpose X or whatever. So if you look at this, and you write down the necessary and sufficient conditions of optimality, assuming Q is positive definite, you get what is called a complementarity problem. Right? So if you have something in X here, let's say you had X transpose Y, you'll get an X there. Right? And so traditional approaches have been, I'm going to solve this in this form. But if you look at this, this is called a mathematical program with complementarity constraints. Most solvers can get you stationary points at best, okay? And that's what NLPEC does. NLPEC will just, is a solver by Michael Ferris. They reformulate this, and they get you some stationary point. On the other hand, the implicit approach recognizes the convexity in the lower level and essentially does not destroy that, right? It doesn't destroy that. As a consequence, you actually have access to global minimizers, okay? Because this problem is actually non-convex, but the implicit version is convex, okay? And so how do we know it's the global minimizer? You can use a global optimization scheme, right? So this is Barron, which is the well-known global optimization scheme. You can see we get very close to that. And in fact, the global solver doesn't scale very well because it uses branching, okay? And so in this case, when this function is convex, the implicit schemes can actually get you global minimizers. And so we also tried this on a host of other kind of MPECs in the paper. So if you're interested in the two-stage and single-stage, we've been able to kind of characterize the guarantees. And so this paper came out in math programming in 2023. And we've been able to extend this work to deal with more relevant problems in learning. So this is a problem on games. I won't get into it here. But recently, we've been able to extend this to federated learning, where we looked at non-differentiable, non-convex, and hierarchical federated learning. And so in that setting, you can again use these types of gradient estimators. And you can quantify both the communication and the complexity guarantees otherwise. Okay, so I have around 10 minutes, right? Or 5 minutes.
Yeah.
Okay, so the last part of the talk that I want to, and so this is very recent work, which is not complete. So we've just got a conference paper. I want to kind of just talk a bit about it. So Gaussian smoothing has been there for, as we've heard, for the last 120 years at least. And so the question has been, can you improve the bounds for Gaussian smoothing, right? So all the bounds that were improved for spherical smoothing by leveraging a concentration inequality. And the question that we were interested in was, can you do something for Gaussian smoothing? And so the idea was to try and revisit this problem. Okay, so if you look at standard Gaussian smoothing, the estimator looks like this, right? As I mentioned earlier. The gradient estimator, if you look at a gradient of f eta of x, is something like n over eta expectation of f of x plus eta v minus f of x plus minus eta v over norm v times v. Okay, so that's the standard estimator. It turns out, and I'm not going to put the proof here, it turns out just by looking at that integral and going through a convolution argument where you change variables, it turns out that you can come up with this estimator. And let me tell you what this estimator is, okay? So this estimator essentially says you generate the Gaussian random variable, which is basically a bunch of independent Gaussians, and you generate exponential random variables. And using that, you've got a slightly modified estimator. You have xi, x minus I minus z minus I, and xi plus eta times the square root twice the exponential. Now, it's a very odd-looking estimator. But it turns out that this estimator isn't completely, it's just from the integral and doing some analysis. Okay, and so once you look at this estimator, and this is what the estimator looks like, right? So unlike the standard estimator that you get, what do? You generate a Gaussian random variable, you enter that into the oracle, and you generate function values. So the same thing here with one caveat, you need to generate exponentials as well. Now, for those of you who've done a simulation or a Monte Carlo sampling course, you know computing exponentials is quite cheap. If you have a uniform, an exponential random variable is just negative log 1 minus u over lambda, or negative log u over lambda, right? Where lambda is the parameter, u is the uniform. So it's very cheap, okay? And but why do it? Well, it turns out, first of all, this satisfies the bias properties, but this is important. It cuts the bound from n squared to n, right? So if you go, so these are the results by Nesterov and Spokojny. Okay, so if you look at the second moment here, you can see this is order n squared. We're able to come down to order n. So don't look at this one. This is actually spherical. Okay, spherical actually has been improved. I didn't update that. So this is L0n. And now you also have benefits here. If you look at the quality, and this is something that Albert, you'd be interested in, the quality of the gradient approximation, at least as per Nesterov's result, was n raised to 3 over 2 times eta. Turns out we can bring this down to eta times square root n. Okay, now the question is this, is this somehow, is it an improvement, but you don't really see it? It turns out you actually see it. Okay, so several points are worth making here. When you actually do the sample complexity, the iteration complexity is order n better than Nesterov's. The sample complexity is similar. It's in terms of n squared. Okay. And when we actually did the numerics, right? So this is, as I said, is ongoing work. When we looked at, in this particular case, convex, and we've got results for non-convex as well. So this is just a convex problem with a L1 penalty. And you can see the error here is 1.19, this is 0.1 in the same number. So it's a factor of 10, okay? And you can see it here as well. Okay, so there are significant improvements without doing anything. I haven't done any kind of, we haven't done tuning or anything. This is fairly kind of just use the estimator as it stands, okay? If you do this for strongly convex, you can see even more improvements, okay? And so the point is that, and so we're interested in using these estimators, not just for optimization, for derivative estimation. So those of you familiar with stochastic simulation, you'll know that these kinds of, for derivative estimation, people have used tools like these, not exactly these. And the question is, can we start using these types of more refined estimators, not just for optimization, but for derivative estimation, and maybe for other types of problems like RL or others, where it might have value. I don't know that. So this is something that just came out in the Winter Simulation Conference, and it's with my colleague, Prakash Chakrabarti at Penn State, and his student, Mingray Wang. So I'll stop here. I think I've hit 4:20. Okay.
Questions?
Jeff?
So in the accelerated Nesterov scheme, or the scheme that had acceleration in it, the plot red curve showed these kind of wiggles that I've seen.
Yeah. And there's a very standard in Excel.
Restart methods, where you look to see if the momentum.
Yeah.
Does it work in this?
I haven't tried it, but that's a good question. This was kind of, our focus was really at this point, get the vanilla scheme. But there are lots of things that we can do to improve that, but we haven't revisited. This is what you meant, right?
Yeah.
Yeah, we haven't done that. Yeah, it's got this strange periodic behavior. I mean, not periodic, it's got this strange kind of oscillatory behavior. Yes, Laura?
So you showed that you could save a factor of square root of n.
Yeah.
Using this new estimator.
Yeah.
Is there any lower bound that like?
Yeah, that's a good question. So we were thinking about that because clearly, when we did spherical, we didn't know the lower bound, but clearly it wasn't the lower bound. It was order n squared. It came down to order n. Question is, how much lower can it go? And I don't have an answer to that, but it's a question. I should say that in the case of this, we've changed the estimator, right? It's not that we've taken Gaussian smoothing and tightened the analysis and gotten a better bound. We've changed the estimator.
Minimax kind of lower bound.
Oh, no, I know there may be. But all I'm saying is that it may be that somehow with some tighter analysis, Gaussian smoothing could be improvable. I just don't know that. I'm not sure. What I do know is that this estimator with a fairly kind of standard analysis, well, we were able to kind of get an improved bound, which actually manifests, right? Because if you think about it, if the moment bounds are lower, you're getting less kind of noise in terms of the gradient estimator, and you're able to get far more accurate solutions. And that's emerging in the numerics.
We should definitely talk. But my question is on the numerics that you showed, you had eta in Gaussian smoothing and eta in your estimator.
Could you repeat that? In the eta?
Smooth pulse. Using your weight, right?
Which one? Wait, no, I smooth. So in one case, I keep eta fixed. In the case where, in that accelerated scheme, I drive eta to 0.
So in your final numerics that you showed,
Yeah.
with your improved estimator,
Oh, yeah. There, that eta is fixed.
it's the same for Gaussian smoothing and your.
Yeah, it's the same. I'm not changed. Yeah, that's the same.
Because you might be able to, I mean, if. you
Modify
change-
it.
I don't know.
Yeah, but then if you do that, what happens is if you modify the eta like that, usually what happens is the manifestation of the eta shows up somewhere else, right? Because I didn't put it here, but when you actually get the error bounds, right? The eta is going to show up somewhere. And the thing is, if you divide by n, yeah, there's no free lunch there. You're going to be hit right downstream. Yeah, Vijay.
Yes, trying to understand what's the difference between your spherical and Gaussian, because in high dimensions, they look the same. Pretty much all the mass of Gaussian systems.
Yeah, that's a good question as to whether, and so this is, I guess what Albert was asking, is there something in the analysis on the Gaussian side that we're missing in terms of tightening the analysis? I don't have an answer to that. I think there are some tangible reasons why we use one versus the other. So for instance, if I tell you that the function is only defined in a certain domain, you do not want to use Gaussian smoothing, right? So there are some settings where Gaussian smoothing is just not advisable. And in fact, it won't work because the function is not defined beyond a certain point. But in terms of its properties, you're right. I mean, they could well be. And that's why I think a lower bound might be useful because it will tell us essentially, is this is this an agenda worth pursuing? And in fact, when we start thinking about this, that's, our initial thought was to try and see whether we could improve Gaussian smoothing just in terms of the moment. And then after a bit of analysis, it turns out that we could actually come up with a modified estimator, which wasn't significantly costlier.
Just a comment in there, and you use exponential, you're actually taking the square root of the exponential. It's a Raleigh actually.
Yes, this one. Yeah, you're right. It is. Yeah. I'm taking a square root of an exponential there. That's right.
Which is like the absolute value of a two-dimensional Gaussian. If you look at the absolute value, it can
Interesting. I didn't think about that. When we simulate it, we're just using exponential, I should say. Yeah.
just a side random comment.
Well, that's interesting. Jeff, you had a question?
Nice talk, by the way. So when you compare the stochastic gradient descent with the stochastic quasi-Newton, the SGD eventually did this oscillation, but it went down faster initially. Is there any benefit to a, hybrid approach where you get that initial and then switch?
Yeah, so that's a good question. I mean, I also want to be a little careful about reading too much into these trajectories, right? I mean, I don't know if, I'm not one of these folks who's done tons of computation to give you a clear answer about does SQN all. What I do know is that if you look at the complexity guarantees of SQN, they're pretty poor, particularly in terms of the dependence on the Lipschitz constant. And so people always look at it and say, well, why should I even use it? And in our earlier work where we looked at accelerated schemes for stochastic optimization, again, we weren't able to kind of compete with the Nestrov's 1/k². But when you actually compare the empirical behavior, it's quite good. And so I think the thing is I think complexity guarantees are useful as a guidance, but I think if you use them entirely to kind of discern or chuck out algorithms, I think we may be a bit misguided there. Yeah, so because increasingly you see this. I mean, those of you who manage papers, you know this. You'll have folks who turn to the last page, check their rate guarantees, and decide whether to accept or decline a paper. It's an extremely cynical approach, and I think we lose a lot as a community if we do that.
Worst case analysis, right?
Yeah, and I think it has some value, but I think if you entirely use that, I think, for instance, SQN or QN schemes would never have been relevant. Right? And I think quasi-Newton schemes are basically the workhorse in most nonlinear programming solvers. Albert, would you agree? Right? In the sub-problem solvers, QN schemes are used all over the place.
Questions? Well, let's thank you, again. And,
Thanks, Jim. Sorry, I unloaded a lot. You did? Okay.
Gradient thing. Something I did 3 years ago. I don't remember what it was. I just remember having to learn about it. Something that
Hi.
I had to do to set.
Oh, really?
Value.
Yeah. I think it's actually extremely prominent in control theory, right?
Yeah.
Because especially the switch system folks, and I know they use it a lot. In fact, if you look at the work by Frank Clark, he actually does a lot of work on non-smooth systems.
I don't even remember what I was doing. I just I had to
It was
learn
useful.
about it. So.
Hi. So I have to be careful, right? So when you have that, right, that claim is true if the complementarity form has a unique solution. So if I wrote it like this, what's your name, by the way? Yes, Sive. How do you spell that? Shinbe. Okay. So if you look at this, suppose I had this as the complementarity form, right? So if this has a unique solution, which is basically, given by whatever, the solution to some VI or Rn plus, and, whatever, something plus Nx or whatever. So if you had that, then you could substitute this back inside here. And if you knew this was convex, or if you could prove it was convex in X, then you could get global minimizers. But in general, you cannot. So the thing is that this is the implicit formula. It gives you a vehicle for computing a global minimizer if the implicit function is convex. Because the function in the full space need not be convex. But in the reduced space, it may be convex.
Given that
This has to be single valued, but it's not just single valued. It has to be convex in both arguments. Okay. So the problem that I looked at, the Stackelberg problem, actually satisfies. Let me just say, Eoff, hey, we have to get together. I'll send you an email. Yeah, we're right on the corner.
Oh, yeah.
See ya. Yeah. So if you look at the paper, you send me an email. I'll send you a link to the paper. Okay. Are you a faculty member in?
We'll chat about the
Okay.
results.
In double E?
I think we did really well.
Yeah.
I'm getting so old now. Younger people might be faculty members. They might be deans for all we don't know. You Shinbe, send me an email. I'll send you the paper. I'm enjoying. I unloaded a lot, so yeah, we'll talk on. Yeah. Okay. Good. Thanks a lot for coming.
Look, in the middle of your talk, I get a phone call. Guess
Oh.
who? Prashant calls me. He says, I told him, you can't take the call now.
That's funny.
I know, it was-
We have to get him to come down. He's
Yeah,
not
yeah.
far away.
Nice talk.
I'm glad that you enjoyed. How are you doing?
Well,
Yeah, I've been just keeping afloat. We have to get together.
yeah, we should do that. I know.
I'm teaching in this class actually.
Wait, you're teaching here?
Yeah, so it's interesting you told me because I'm teaching stochastic simulation the first
Yeah,
time.
you were
So
telling me.
I'm epsilon away from the students, as you must have realized when you told me the square root of exponential that I didn't know.
That's okay.
I was telling Peter
That's
Glynn this,
mine.
that said I pity the students because I'm literally epsilon ahead of the students. But the epsilon, and he said, I'm like that. I said, no, you're not. But anyway, it's very sweet of you to say so. But it's
First time you teach it, it's usually
yeah,
that.
it takes a bit of time because I don't use everything in it. There are all sorts of things that I don't use. But it's good. I'm learning. So how are you doing? What are you teaching?
I'm teaching it's like a,
All right, the nonlinear control.
no. It's teaching, not nonlinear control. I'm teaching what's an ABET course. It's like major design professionalism, like a 2-hour lecture.
They come to the right person.
I don't know.
So I wanted to ask you, Vijay,
Yeah.
this RL problems, I know they use zeroth order schemes.
They use a lot of zeroth-order.
I'm curious.
Yeah, even actually, lay student just presented something on that. I was curious for a different problem, whether, I mean, somehow it came up as a discussion in the defense. Actually, it was there, but I mean.
There you go.
Oh, I'm glad you enjoyed Salah. So let's, are you around? Just give me 2 minutes. I want to talk to you.
Oh, you-
Okay, then you should go. Then I'll email you. I want to talk to you about next week.
Okay.
Okay, cool. I have to go for some, I'm on some college non-evaluative committee. And, you know, somebody's coming at 5:10. There's this guy from Nuke that they're trying to hire who's from Penn State. So now I think there's an exodus. So they just told me you go meet this guy. I'm like, okay. So, but it's in Cooley building. So I don't know whether, I think that's somewhere that side, right?
Julie is down there.
Somewhere, okay.
Not far from your office.
Okay. I need to reach out to Lay as well. You know, that day this guy had come, Jeff student. So I came up, what's his name? No, he's a Korean guy.
Yeah.
So Lay's office was there, I knocked, but he wasn't there. But are you in the same corridor there?
No, I'm on the other side.
Okay, so I thought I'd walk around, but I thought they'd think I'm a homeless guy and get rid of me or something. But
But anyway, so one of the things I was curious for other reasons was,
There was
like, zeroth order is one thing to do, but maybe some Gaussian process optimization might be better in some context. But the problem is most of the results are using IID stuff. And we want-
oh, I don't know this yet. This is an area I'm not as knowledgeable about. I don't want
But
to.
zeroth order optimization, he was looking at for a two-sided market.
Okay.
It's possible to do it for a one-sided.
So I don't know much about, as you know, I know nothing about learning, but apparently now they're using these diffusion models to train these things.
Yeah.
So is that your kind of thing?
Not yet, I haven't looked at division models yet. I mean, I will look at it for some other reason, but I was interested in. I was supposedly doing some work. Neither of us done anything.
So actually, the reason we started doing this was. I think I was explaining that first order. Problems, not problem, one of the issues when you prove these limit, and as you well know, is that C2. If the function is expectation value.
Yeah,
You
then
need some
you want
C2
some partial convergence theorem.
Yeah. But the problem is that most of the problems we're looking at are non-smooth.
Yeah.
Right? What happens is that if you use this change of variable argument, you need the C2 properties move to the density. And so in estimate came out. The derivative. Then with a bunch of analysis, you're able to come up with this
Yeah,
estimate.
because density, I mean, that's nice. Gaussian density is nice.
Nice. And you can see that's why this is showing up here. So that's something that you are actually recognize immediately.
Yeah, because then you get x times e to the sum
Exactly.
squared, which is essentially where your the Raleigh comes.
Yeah.
in.
So
Yeah, I mean, that's pretty clear, the Raleigh comes in
my
there.
thought is to see whether we can use these ideas for also proving clean limit theorems for non-smooth problems. Because that's been the one issue. You can't do it because almost all of the. Yeah, see around. Yeah. We were surprised. In fact, this was a bit serendipitous. That it works because you know how it is. You get back to it. Very manifests in terms of improved behavior.
Yeah.
Particularly for stochastic schemes, which are notoriously But these, without too much tuning, we were quite surprised. So, and so I do think that there is value in.
I'll say next week, by the end of the week, and then but you'll handle the emails.
Yeah, no, that I agree.